faculty at ACE Engineering Academy. In this live session, we are going to talk about the important concepts that are useful for various competitive exams like Transco, GENCO, DISCOM. Okay, so here I'm going to take some important concepts of signals and systems, that is the Fourier series topic. Now, before I get into this discussion, I have an important notification for you, important message for you. Now, just few days back, that is, look at this notification from Southern Power Distribution Company of Telangana Limited. So, this notification is dated 09/05/2022, that is few days back. So this starts, the application starts from 12th, that is 12/05/2022, and what's the last date for the payment? It's 03/06/2022. And when is this exam held? So SPDCL exam is held on 17th, that is 17/07/2022. So hardly we just have we have hardly 2 months. So if you are preparing consistently, you will definitely crack this exam and many exams like this. So it has clearly provided in the notification about the date of examination, right? All the details are provided. Let me also show you the syllabus. So it has provided the syllabus as well. So in the syllabus, so here we are. So this is the topic that I'm going to discuss. In this, I'm going to focus on the Fourier series representation in today's lecture. So this is the syllabus. You can go through it and you can apply for that. So let's get into the discussion. Now in this live session, I'm going to talk about the Fourier series representation for periodic signals. The main discussion will be on how to identify the symmetries present in the periodic waveforms. So let's start this analysis. So the topic is Fourier series. So what's a Fourier series representation of a periodic signal? So let's write the Fourier series representation of a periodic signal. So how do you write it? Suppose if you consider a periodic signal with time period capital T, its Fourier series is given as follows. It's A0 plus summation n from 1 to infinity, it's an cos n omega naught t plus bn sin n omega naught t. Okay, sin n omega naught t. So this is the Fourier series representation of a periodic signal. How do you find this A0? How do you find this An? How do you find this Bn effectively? Okay. Suppose if I give you an even periodic signal, how do you find this A0, An, Bn? Suppose if I give you odd signal, how do you find all these coefficients? Suppose if I give you a half wave symmetric signal, how do you find A0, An, Bn? That's the discussion for today. So now, what is this omega naught? Omega naught is the fundamental frequency which is given by 2 pi by capital T, where capital T is a fundamental time period. Let's now comment on what is the expression for A0, An and Bn. So how do you find this A0, An and Bn? Let's check it. So A0 is calculated in the following way. So look at expression for A0. It's 1 by T integral over one fundamental period. So we write like this. The meaning is you need to integrate over one fundamental period. So what are you supposed to integrate? F of t dt. So this is like integrate the periodic signal in one fundamental period and then divide by that fundamental period. If you do this, you are going to get the average value of the given signal. We also call this as DC value, or you can even call this as the constant term in the Fourier series representation. So the familiar words are, this is called the average value. So what is this called? This is called the average value. It's also called DC value. So how do you find this? To find this, we need to integrate this function over one fundamental period and then divide by that fundamental period. For example, if I write the duration like this, if I say the duration is like 0 to capital T, so how much is this interval? obviously from 0 to capital T, the duration is capital T. Suppose if I say the duration is like taken from minus T by 2 to T by 2, so how much is the duration? Right, from minus T by 2 to T by 2, it's obviously capital T. Right, for example, let's say you have considered from T naught to, let's say, T plus T naught. So how much is the duration? The duration is again capital T. So it doesn't matter whether you integrate from 0 to T or minus T by 2 T by 2 or T naught to capital T plus T naught. In all these cases, the duration that you have taken is capital T. Now why is this? Because the given signal or the considered signal is periodic. So it doesn't matter in which interval you choose. So sometimes I take 0 to capital T, sometimes I take minus T by 2 to T by 2. Now there are some advantages when you take from minus T by 2 to T by 2. So I'll just show you those advantages. So this is how you find A naught. What next? How do you find An and Bn? Let's look at the expressions for An and Bn. Look at the expression for An. It's 2 by T integral over T. It's f of T cos n omega naught T dt. So this is how I find An, which is the coefficient of cosine term. How do you find Bn? It's 2 by T integral over T. It's f of T sine n omega naught T dt. So this is how I find An and Bn. Now what are we going to say is, how do you find, or how effectively you can find this A naught, An, Bn for various symmetries? Various symmetries like even symmetry, odd symmetry, and then half wave symmetry. So from today's live lecture, I am very sure that you will know how to identify the symmetries. So my focus is on how to identify the symmetries. So now before I proceed with the symmetries, what I would like to do is, I just want to show you some basic operations. Suppose if I give you, let's say if I give you a signal like this, let's say f of T like this. Let's also draw this. Let's draw this. Let's say this is 0, this is T. Let's mark this as 1. So I have drawn a signal f of T. Now how do you, or if I ask you to rotate this about the y-axis, how do you do that? If I ask you to rotate this about x-axis, how do you do that? So let me show you how to rotate this about y-axis. Now take this, do this rotation about y-axis. So what are you going to get is a signal like this, which is from minus T to 0. So here the value is 1. So whenever you rotate a signal about y-axis, then such whatever you get is called the time reversal. So what is this called? The time reversal of f of t. You can call it as time reversal of f of t, or simply the rotation of f of t about y-axis. So let me write this. So what is this? This is the time reversal. Time reversal of f of t. Or you can even call this as rotation of f of t about y-axis. Now apart from this, I would also like to show you how to rotate this about x-axis. Okay. So here we have the considered signal like this, which is from 0 to capital T, whose value is 1. So what is this? This is f of t. Now what I'm asking you to do? Rotate this about x-axis, right? So this is the x-axis and you need to rotate this about x-axis. Let's do that. So what are you going to get? When you rotate this about x-axis, so this is what I'm going to get, something like this, which is from 0 to capital T, but this time the magnitude here is minus 1. So what is this called? This is called rotation about x-axis. Mathematically, this is denoted as minus f of t. So now I just showed you what is rotation about the y-axis, rotation about x-axis. So this will help you to understand the symmetries. So let's see how do you write the Fourier series of an even signal. So our next topic is how do you write the Fourier series of an even signal. So now what do you mean by even signal? So when do you say that a signal is even? So whenever it satisfies this property, that is f of minus t same as f of t. A signal which satisfies this, that is f of minus t same as f of t, is called a even signal. Now I'm saying that let's consider a signal, a periodic signal which is even. What will happen to its Fourier series coefficients? In the same way, I'll see what's the Fourier series of an odd signal. In the same way, I'll also see what's a Fourier series of a signal, periodic signal which has got half wave symmetry. So we will discuss these things, and then I'll be presenting you the various waveforms, and let's look at what kind of symmetries are there, what will happen to the Fourier series coefficients. So that's the discussion in this live session. So let me look at what is A naught. So what's the expression for A naught? It's 1 by t. I said integrate it over one fundamental period. I can write it as minus t by 2 to t by 2 f of t dt. Now you can see that the given signal is an even signal. So you are integrating an even function from minus t by 2 to t by 2. So what you can do is you can write this as twice. Okay, you can write this as twice, that is 2 by t integral 0 to t by 2 f of t dt. So this gets simplified like this. What about an and what about bn? So let's try to simplify those things. Let me now comment on an. The expression for an is 2 by t integral minus t by 2 to t by 2. It is f of t cos n omega naught t dt. Now we are looking at a case where the given signal is even. So f of t is even, cos is also even. When you multiply an even with another even, what happens? The resultant is also even. So this is even. If you are integrating an even function, then from minus t by 2 to t by 2, you can simplify this and write it as twice 0 to t by 2. So there is already 2 here. So what I get is 4 by t integral 0 to t by 2 f of t cos n omega naught t dt. So this is what is the expression for an. We have simplified an. Now the most interesting thing here is what's the value for bn. So let's look at what is the value for bn. The expression for bn is 2 by t integral minus t by 2 to t by 2. It is f of t sine n omega naught t dt. Now we have assumed that f of t is even, sine is odd, this is even, this is odd, even into an odd will result in an odd function. So now this is odd function, and you are trying to integrate an odd function from minus t by 2 to t by 2. So what will this will give you? This will definitely give you what? 0. That means in the Fourier series representation of an even signal, you don't find any sine terms. What you will find is the constant, that is the DC value, and then the cosine terms, right? So now I want to summarize this. So the Fourier series of an even signal contains the DC value as well as the cosine terms. There are no sine terms. So let me write that. So this gets simplified as a naught plus summation n from 1 to infinity, it's an cos n omega naught t. That's it. There are no sine terms because bn is 0. So finally, what's the comment? The comment is Fourier series contains DC and what terms? Cosine terms. Now this kind of questions were asked in various competitive exams. So just by looking at the waveform, you can decide what terms are present. So if it's an even signal, DC and cosine terms are present. What next? Let's look at what the Fourier series of an odd signal. Okay, so let's quickly see what the Fourier series of an odd periodic signal. Okay, so let's find a naught, an and bn. Okay, so what is expression for a naught? It's 1 by t integral minus t by 2 to t by 2 f of t dt. So now clearly whatever we have assumed is a odd signal. So what do you mean by odd signal? Any signal which satisfies this f of minus t equal to minus f of t is a odd signal. So what will happen? Now this is an odd signal. You are integrating an odd signal from minus t by 2 to t by 2. Obviously this will give you what? It will give you the answer as 0. Let's see what will happen in the case of an. So what do you think this is going to happen? So it's 2 by t integral minus t by 2 to t by 2. It's f of t cos n omega naught t dt. Now we have assumed that f of t is odd, cosine that is cos is even, odd into even will result in an odd function, and you are integrating an odd function from minus t by 2 to t by 2. So what will happen to this result? So let me first highlight that this is odd. This is odd. You are integrating an odd function, so obviously the answer is 0. So interestingly, for an odd signal, a0 is 0, an is also 0. Now let's find bn. Okay, so let's see what happens for bn. The expression for bn is that it's 2 by t integral minus t by 2 to t by 2 f of t sine n omega naught t dt. Now what did you assume? We have assumed that f of t is odd. So this is odd, this is also odd. When you multiply an odd with another odd, the resultant is even. So this is even. So you are integrating an even function from minus t by 2 to t by 2. So you can write this as twice 0 to t by 2. So since this is even, you are integrating from minus t by 2 t by 2, you can write twice of 0 to t by 2. So there is already a 2 here, so if you multiply 2 more, so it's like 2 into 2, which is 4. So it's 4 by t integral 0 to t by 2, it's f of t sine n omega naught t dt. So now what's the final conclusion? The final conclusion is that in the Fourier series of an odd signal, there is no DC value, there are no cosine terms, what we see is only sine terms. So let's write that in the Fourier series of an odd function. So what happens? So if I write the Fourier series representation, it looks like this. Summation n from 1 to infinity, it's bn sine n omega naught t. That's it. So what's the comment? The Fourier series contains only sine terms. So let's write that comment. Fourier series contains only sine terms. So far we have seen even signal, that is Fourier series of an even signal, Fourier series of odd signal. It's time to see the Fourier series of half wave symmetrical signals. So let's put this heading, the Fourier series of periodic signals, with half wave symmetry, half wave symmetry. So let's first see what's the condition for half wave symmetry. Let's see what's the condition for half wave symmetry, and then we will try to simplify this. Now whatever I'm going to discuss, this has been asked in many of the competitive exams. So the end results are very, very important for you. Firstly, like what's the condition for half wave symmetry? Like we said, for an even signal, f of minus t is same as f of t. For an odd signal, we said f of minus t is minus f of t, like that. What's the condition for half wave symmetry? The condition is that f of t is equal to minus f of t plus or minus t by 2. So this is the condition for half wave symmetry. So what are the operations involved here? Right, there is a minus sign here and there is a shifting operation here. So this minus sign means there is a rotation about x-axis and there is a shift. Okay, so you have to shift by what amount? T by 2, that is half the time period. So there are two operations involved. One is the rotation about x-axis, the other is the time shift, that is by t by 2. I'll explain this, how to identify the half wave symmetry in a detailed way by taking various examples. Before that, let's see what happens to the Fourier series coefficients. So let's quickly see that. we understood that there are two operations involved in half wave symmetry. That is, there is a rotation about x-axis as well as there is a shift by half the time period. Now, I would like to comment on what is A0, what is An, what is Bn. So, have a look at this. A0, it's the same like 1 by t. Can I write 0 to t f of t dt? Yes, it doesn't matter whether it is minus t by 2 to t by 2 or 0 to t. Just have to integrate in one fundamental period. So, can I split this in the following way? Can I split this in the following way? That is 1 by t, 0 to t by 2, okay, 0 to t by 2, it's f of t dt plus t by 2 to t f of t dt. I can split like this. Now, what I'll do is, have a look at this. So, there are two terms involved here. One is from 0 to t by 2, the other is from t by 2 to capital T. I'll try to simplify this part now, okay. I'll just take this particular thing and I'll try to simplify this. So, see this, t by 2 to capital T, this is f of t dt. Now, clearly we said that we are looking at a case where the signal has got half wave symmetry. What do you mean by half wave symmetry? F of t is same as minus f of t plus or minus t by 2. That means in the place of f of t, I can now substitute minus f of t minus t by 2 or t plus t by 2, doesn't matter. So now in the place of f of t, I am going to substitute minus f of t plus or t minus t by 2. So have a look at this, minus 0, what are the limits? T by 2 to t f of t minus t by 2 dt. So I want to substitute this. What next? I just want to see what will happen to this A0. Okay, so you can also comment in the chat box what will happen to this A0. What do you think is going to happen to this A0? So I'll go for a substitution like this. Let's say t minus t by 2, let's say this is b x. If you differentiate on both sides, you get dt equal to dx. Now with the substitution, what happens is the limits will change. So if you substitute the lower limit here, that is t by 2 minus t by 2, it's 0. That means the lower limit of x is 0. Now if you substitute this capital T here, t minus t by 2 is t by 2. So the upper limit of x is t by 2. So let's do this simplification part. So what are we going to get? So this gets simplified as, there is a minus sign, the limits change 0 to t by 2, and then this is f of x dx. This is f of x dx. Now see this, how is this going to help us? Right? You highlighted this part, you said you took this, you simplified this is equal to minus 0 to t by 2 f of x dx. So if you put this here, they both cancel because of the minus sign. So this and this are like, see, except for the minus they are equal. So then when you put this here, obviously they cancel. What are you going to get? You are going to get A0 as 0. That means if a signal has got this half wave symmetric nature, the DC value or the average value is 0. Okay. What next? I want to comment on what would be AN and BN. This A and BN are very interesting results. So how do you find this AN? Look at this. What's the expression for AN? It's 2 by t, let's say 0 to t, f of t cos n omega naught t dt. This is the expression for AN. So I would like to split the integral. So let's see what happens. This is 2 by t, 0 to t by 2. It's f of t cos n omega naught t dt plus t by 2 to t. Okay, I'm just splitting the integral. So it's f of t cos n omega naught t dt. So now what's going to happen, right? Do you know what is going to happen for AN? You need to simplify this to know that. So let's simplify this. What will happen to AN? So what I'll do is, I'll consider this particular part. I'll try to simplify this portion. So how does that look? So look at this. I'm just considering what is highlighted there. It's t by 2 to t f of t cos n omega naught t, cos n omega naught t dt. So what will I do is, I'll substitute in the place of f of t minus f of t minus t by 2, because the given signal possesses half wave symmetry. We have assumed that the signal has got half wave symmetry. You can replace f of t with minus f of t minus t by 2. So let's do that replacement. So if I replace that, I get t by 2 to t, there's a minus sign, f of t minus t by 2 cos n omega naught t dt. If you can cleverly simplify this, the same thing can be applied even for bn. So let's carefully simplify this. What next? What have you done here? You have gone for the substitution. The same thing will be done here. Let's go for the substitution. So you are going to get some beautiful results at the end. So what substitution? I would like to take t minus t by 2 as x. Differentiating both sides gives you dt equal to dx. Will the limits change? Of course the limits change. You take this, put it here, t by 2 minus t by 2 is 0. You take the upper limit, put it here, t minus t by 2 is t by 2. I have the new limits now. So this integral is simplified like this. There's a minus sign, so this is going to play a crucial role. There's a minus sign here, 0 to t by 2. And then it's simply f of x. What next? What next? Cos n omega naught. In the place of t, what can you substitute? In the place of t, what can you substitute? In the place of t, I can substitute, if this goes here, it becomes x plus t by 2. It becomes x plus t by 2. That's what I'm going to substitute here. X plus t by 2 and then dx. Let's multiply, okay? So we need to simplify this part. If I simplify, I get minus 0 to t by 2 f of x cos n omega naught x plus this n omega naught is also multiplied to this, so it's n omega naught t by 2. So this is what I get. Now what do we know about omega naught? Omega naught is something like this. Omega naught is 2 pi by capital T. So can you tell us what is this omega naught t by 2? If you want omega naught t by 2, send this t the other side and then take this 2 to the left side. So what is left over is pi. Let's substitute that pi here. Okay, so let's substitute the pi here. So what are we supposed to get? So we get something like minus 0 to t by 2 f of x cos n omega naught x plus n pi. Because in the place of omega naught t by 2, we have substituted pi. So this gives you n omega naught x plus n pi. Now this n will decide the value, or n will tell us what will happen to this an. So what I'll do is I'll take some even numbers. Let's assume n to be even. And in the other case, let's assume n to be odd. And then we will analyze. So for example, let me first start with even numbers. So where are we? So we are trying to simplify the value of an. So in that process, I'm trying to simplify this part. So I just took this, I'm simplifying that. So we are just 2 more steps away from the result. If n is even, what happens? Right? So let's take n, case 1. n is even, what happens? N even like 2, 4, 6 and so on. So when n is even, for example, if you substitute 2 here, it's like 2 pi. Cos 2 pi plus theta. What is cos 2 pi plus theta? Cos 2 pi plus theta is simply cos theta. How much is this? It's simply cos theta. So let's write like this. 0 to t by 2, and don't forget about this minus. This is f of x cos n omega naught x dx. Suppose if you take 4, cos 4 pi plus theta is also cos theta. So when n is even, this is simply cos n omega naught x. And there is a minus sign. And the limits are 0 to t by 2. If you substitute this in the place of this, if you substitute this here, they both cancel. They both cancel. That means the value of an will be 0 whenever n is even, meaning by there are no even harmonics in this discussion. What will happen for sine? For sine also the same calculations. right? Instead of cos, you will have sine, the same observations. So when n is even, the sine even harmonics will also vanish. Now let's look at the other case. What's the other case? Suppose if n is odd, what happens? So this is case 2, where n is odd, something like 1, 3, 5 and so on. What happens when n is odd? When n is odd, for example, put pi, cos pi plus theta, cos 3 pi plus theta and so on. What is cos pi plus theta? It is minus cos theta. Now when you write minus cos theta, this minus and there is additional minus, they cancel, and what you get is something like this. There is no minus now, it's 0 to t by 2, it's f of t or f of x, let's say, because it's in x, f of x cos n omega naught x dx. So this is what I get whenever n is odd. So because n is odd, so this gives you minus cos theta, minus minus cancels, and this is what you have to substitute in the previous expression. So what's the previous expression? The previous expression is something like this. So in the place of this, you will now substitute what are you going to get? So t by 2 to t, f of t cos n omega naught t dt, in the place of this, you will again substitute a similar expression like this, that is 0 to t by 2, f of t cos n omega naught t dt. That means this time they don't cancel, but they add up and you get 4 here. So that's what I'm going to write now. Check this. So when n is odd, so let me summarize now. So we have understood what's happening for an. So let me summarize what's happening for an. So an, the value of an, it's 0 whenever n is even. And how do you find when n is odd? Okay, so when n is odd, how do you find it? So when n is odd, it's like 4 by t, 0 to t by 2, it's f of t into what? So let's write like this. So 4 by t, 0 to t by 2, f of t into cos n omega naught t dt. So it's very clear that all the even harmonics are vanishing, cosine even harmonics, and then we have only the odd harmonics. The same observations can be seen for even Bn. So what's happening for Bn? Bn will also be like this. So it's 0 whenever n is even. Now what you can do is, in this derivation process, wherever there is cos, you can put sine, and then you will see the same results. You will get the same results. So the value of Bn would be 0 whenever n is even, and it is 4 by t, it's 0 to t by 2, it's f of t sine n omega naught t dt. And this is true for what? When n is odd. Okay. So finally, what's the comment? The comment is that whenever you are working with half wave symmetric waveforms, A naught value is 0. What about An? An is also 0 for even n, and you have to find the value of An whenever n is odd. Okay, whenever n is odd. What for Bn? Same observations. For Bn also the same thing, that is it's 0 whenever n is even, and you need to find the value of Bn whenever n is odd. So what's the comment now? The comment is that A naught is 0, right? All the even harmonics are gone, only odd harmonics are present. Let's write that comment here. The Fourier series contains only the odd harmonics. Fourier series contains only odd harmonics. So that's the conclusion. What next? Let's summarize all these results. That means what happens in the case of even, odd and half wave symmetry, and after that what? The actual discussion, that is, we take the various waveforms and then we'll try to identify the symmetry present in it. So here is a summary based on which there were many competitive exam problems. So what it says is, you have the symmetry, right? Suppose if it is even, the condition for even is f of t is same as f of minus t. So what will be A naught? You need to find A naught. An also you have to find. No need to find Bn because it's always 0. In its Fourier series representation, you will have constant term as well as cosine terms. Suppose if it is odd, right? What's the condition? What's the condition? You can write like this, or even you can write like this, f of minus t same as minus f of t. Both are actually equivalent, no issues with that. And then a0 is always 0, an is always 0, you need to find bn, and in its Fourier series representation, you have only sine terms. Now what's the condition for half wave symmetry? The condition is that f of t is equal to minus f of t plus or minus t by 2, a0 is 0, an is also 0 for even harmonics, bn is also 0 for even harmonics, so you need to find an and bn for odd harmonics. So that's what is highlighted here. So odd harmonics only are present. So now we understood what is happening to the Fourier series coefficients. Now let's take certain waveforms, identify what kind of symmetry is present in those waveforms. So look at the first waveform. This is just for the first few waveforms, is just to identify whether it is even or not. Look at this. Is it a periodic function? Is it a periodic function? Of course, it's a periodic function. So what's the fundamental period of this? Suppose if you draw it like this, again you see the same pattern. So the fundamental period is 2 pi, right? Fundamental period is 2 pi. So the fundamental period is 2 pi. If you rotate this waveform about y-axis, you are going to get the same thing. Try it. If you rotate this about y-axis, you get the same thing. So because of this, it's even signal. Let me show you an example of odd signal. Look at this, the sine function. What's the fundamental period here? Now you can see that this pattern is what is repeating. So how much is the interval length? The interval length is 2 pi. So let's write the fundamental period here. The fundamental period is 2 pi. Is it odd? How do you check? Right? For sure it's not even, because even means, look at this, when you rotate this about y-axis, you have to get the same thing. So that you will not get it here. So I'll show you how to check this is odd or not. So we'll do one small activity. This will really help for the next waveforms. What I'll do is, I'll just draw the given signal in one of the fundamental period. Let's draw the given signal in one of the fundamental period. So let's say this is minus pi, let's say this is pi. So I'm interested in drawing the given signal in one of the fundamental period. So let's mark something like this. I'll just draw the sine function like this. What is this? This is sine t. Now I want to show you how to check whether it is odd or not. The first thing that you do is, you rotate this waveform about y-axis. So this, when you rotate, it goes like this. This part, when you rotate about y-axis, this goes like this. So how does that look? It looks like this. So what is this? A rotation of this signal about y-axis. How do you mark it? You write it like this, sine minus t. You write as sine of minus t. Now you also rotate this waveform about x-axis, okay, about x-axis. So this is a positive peak. When you rotate it about x-axis, this goes down. When you rotate this about x-axis, this goes up. So how does that look? It looks like this. So what I have done is rotation about x-axis. How do you represent it? You represent like this, minus sine t. Now you observe this and this. Are they same? Yes, they are same, right? So now sine of minus t is exactly looking like minus sine t, right? So rotation about y-axis is same as the rotation about x-axis. That means this function is satisfying a property that f of minus t equal to minus f of t. So what kind of signal is this? This is an example of an odd signal. So once again, rotation about y-axis is same as the rotation about x-axis. That's how you check whether it's a odd signal or not. So let's continue. I'll be showing you the various waveforms, and I want you people to comment on the symmetries. So here, for example, let's also check whether this has got half wave symmetry or not. Okay, so this is the signal in one of the fundamental period. Now for half wave symmetry, what you have to do is, you have to shift this part to the next half. That means when I shift this to the next half, I get something like this. Apart from shifting, you should also rotate it about x-axis. When you rotate this part about x-axis, are you overlapping with this waveform? Yes, I am overlapping with this waveform. I'll tell you this again. See, this is the periodic signal in one of the fundamental period. What you do is first consider half of the signal like this, shift this to the other half. I've shifted this to the other half and then I'll rotate this about x-axis. Now when you rotate it about x-axis, is it overlapping with this? Yes. So it's an example of half wave symmetric waveform. So I'll show you a few more examples where let's identify the symmetry present in those waveforms. Have a look at this. What kind of symmetry is present? Suppose if you rotate this about y-axis, again you will get the same signal. Suppose if you say this is f of t and you start finding f of minus t, this will again result in the same thing. That means this is the example of even signal. This is the example of which signal? Even signal. Now when you try to find its Fourier series, in its Fourier series, okay, for sure there is some DC value because you have to integrate that, right? So we can now say that it has got some DC. Now apart from that, since it's even, it will have only cosine terms, right? So I can now say in its Fourier series representation, it is going to have DC plus cosine terms. DC with cosine terms. So the questions are framed based on the symmetry. They'll give you a waveform like this, and in the options they'll say, so the Fourier series contains dash. So in this example, the Fourier series contains the DC value and cosine terms. Let's take few more examples. So now, what kind of waveform is this? Is it even? Is it odd? Or is it half wave symmetry? Let's try to check this. First of all, what's the fundamental period? Right? So if you look at this waveform, it's 1 and then from here onwards it's minus 1. Again you see 1 and then minus 1. So it's periodic. The first question is, what is its fundamental period? Now look at this duration. How much is this? This is 2 units. Look at this. This is 2 more. So now, how much is a fundamental period? It is 4 units. So the first question is, what's the fundamental period? The fundamental period is 4. Let's find the DC value. So how do you find the DC value? Now to find the DC value, you have to integrate this function in one fundamental period. So we understood that the fundamental period is 4 units. Now when I try to integrate this, this is like a positive peak, this is like a negative peak. They cancel out and what you get is 0. The DC value is 0. Now in addition to that, let's see the other symmetries. Now you take this waveform and then rotate this about y-axis. If you rotate this about y-axis, again you get the same waveform. That means this is even signal. It is even. Why it's even? When you rotate this about y-axis, you again get the same thing. So because of this, it's a even signal. Do we have any other symmetries? That's what I want to ask. Do we have any other symmetries? Now if you want to check, that means other symmetries means obviously I'm talking about half wave symmetry. For half wave symmetry, what are you supposed to do is consider the periodic, consider the signal in one of its period. Now look at the first half. Like this is the first half. You shift this to the other half. I'm just shifting it. So if you shift, you get something like this. And then rotate that about x-axis. You need to rotate this about x-axis. When you rotate, is this overlapping with this? Yes. That means this has half wave symmetry. So the DC value is 0. It's an even signal as well as half wave. It has got half wave symmetry. Okay, it has got half wave symmetry. Now what are the comments? The DC value is 0. So when you say even, that means there are no sine terms. There are no sine terms. And you are also saying that it has got half wave symmetry. When you say half wave symmetry, only odd harmonics are present. Now I can finally comment that the Fourier series contains cosine with odd harmonics. Right? The Fourier series contains what? It contains cosine terms with odd harmonics. So that's what I'm going to write. The Fourier series contains cosine with odd harmonics. So you can expect this kind of questions. You can solve this in, let's say, less than a minute. Just looking at the waveform, you will get the idea. So initially we practice like this, but after a few examples, just by looking at the signal, you can tell what kind of symmetry is there. Let me take a few more examples. Look at this. Is it periodic? Yes, it is periodic. What is its fundamental period? So let's try to draw this like this. So you see there's a pattern that is repeated. There's a pattern that is repeated. So what's the fundamental period? So now you can see that this is like a negative peak, this is like a positive peak, and this is what is repeating. This is what is repeating. So how much do you think is this duration? This duration is 2 units. Therefore, the fundamental period of this periodic signal is 2 units. So what's the fundamental period? It's 2 units. What are we supposed to do? We are supposed to look at what is the DC value, what kind of symmetry is present, right? And then what terms are present in its Fourier series representation. So how do you find the DC value? For DC value, I have to integrate the periodic signal in one of the fundamental period. For example, if you try to integrate this and then divide by the fundamental period, obviously the DC value would be 0. So no more calculation. Just by looking at this waveform, I can say that the DC value is 0 without any calculations. Now I want to check whether this has got even symmetry, odd symmetry, half wave symmetry. For that, what we are supposed to do is draw the signal in one of the fundamental period. That means let's draw for 2 units and then let's see what kind of symmetry is present. So have a look at this. I'm going to draw it. So I'm going to draw f of t. So I'll draw from -1 to 1, which covers one fundamental period. So let's draw it. This is -1. Let's say this is 1. Okay. So now from -1 to 0, this is something like this. Let me also mark this. So how is the signal? So it's like this in one of its fundamental period. So what is this? This is f of t. Now what are we supposed to do? We are supposed to rotate this about y-axis. So when you rotate this about y-axis, so this goes like this goes like this. Let's draw that. So if you rotate this about y-axis, what happens? So this part goes like this, that is like this, and then this part goes like this. So you get something like this. Okay. So what is this? This is f of minus t, which is a rotation about y-axis. What next? Let's also rotate this about x-axis. So if you rotate this about x-axis, so this goes down, this goes up. Okay. So how does this look? This goes down. So it's something like this. And this goes up, na? So this is something like this, right? So what is this? This is minus f of t. Now you try to verify what is f of minus t and minus f of t. Okay. So you try to check what is f of minus t and minus f of t. Are they both same? Look at these waveforms. Yes, they are exactly the same. That means this signal has got odd symmetry. The signal is odd signal, right? Let's write that. This signal is odd. Now apart from this, do we have half wave symmetry or not? I want to check that. Do we have half wave symmetry or not? Now for half wave symmetry, what we usually do? Half wave symmetry deals with, there is a shift operation as well as there is a rotation about x-axis. For example, if this is our waveform, this is in one fundamental period. Now what you are supposed to do is take this, shift this to the other half, shift this to the other half. Now when you shift this to the other half, you get like this. I said shift, right? You need to shift this to the other half. So I have shifted. Now after shifting, so let me again show with dotted lines. So we need to shift that. So I have shifted, and after shifting you need to rotate it about x-axis. When I rotate it, I get something like this. Is this overlapping with this? No. That means this signal has no half wave symmetry. So what kind of symmetry is present? Odd symmetry is present. The DC value is 0. Now, in its Fourier series, what it contains? It contains only sine terms. The Fourier series contains what? It contains only sine terms. So that's the conclusion. Let's write that. The Fourier series contains sine terms. So I hope you people are following this. Fourier series contains sine terms and there is no half wave symmetry. Let me take few more examples. Let me explain you about these symmetries. Now this is also a periodic signal. Look, this, okay. So this pattern is repeating. This pattern is repeating. Let me check what kind of symmetry is present. Okay. So let me check what kind of symmetry is present in this waveform. So first thing is I'll find the DC value. So what's the DC value here? I can see that when I try to integrate this and this, so when in the integration process they cancel out and the DC value is 0. So the DC value is 0. Most of the students go wrong in this particular example. So you can actually check your answers with this analysis. So what are you supposed to do? You are supposed to consider the periodic signal in one fundamental period. So I'll draw the periodic signal in one fundamental period. So let's say from minus t by 2 to let's say t by 2 and I'll rotate this about y-axis as well as about x-axis. Let's do that. First of all, let's draw in one fundamental period. So how does that look? It looks like this. So what is this? This is f of t. I have drawn this in one fundamental period. What next? We need to rotate this about y-axis. Let's rotate this about y-axis. What will I get? So this part goes like this. This part goes like this. So let me draw that. So now you need to rotate this about y-axis. So how does that look? It looks like this. And this, right? So how does that look? It looks like this. Now what is this? This is f of minus t, that is rotation of f of t about y-axis. What else we have to do? We have to rotate this about x-axis. So how does that look? Now this goes down, this goes up because it's rotation about x-axis. This goes down. Now when this goes down, it looks like this. Okay? Now this goes up, it looks like this. Okay? It looks like this. So what is this? This is minus f of t. Now you people tell me, is this and this the same? Is this the same? Look, this is like this and this is like this. They are not same. That means this has no odd symmetry. Most of the students, just by looking at this, they feel that it has got odd symmetry. No, it has no odd symmetry. Is f of t same as f of minus t? No. That means there is no even symmetry. Then what kind of symmetry is there? Let's try to analyze. Now, this is the periodic signal. This is the periodic signal in one fundamental period. Okay, I want to check whether this has got half wave symmetry or not. For that, what I'm supposed to do is consider the periodic signal, right? So you just consider this part, shift this to the other half, right? Shift operation. You just have to shift it. Now when you shift it, you get something like this. I have shifted. What next? I have to rotate this about x-axis. When I rotate this about x-axis, this exactly overlaps with this. This exactly overlaps with this, meaning by it has got a half wave symmetry. It has got what? It has got half wave symmetry. So now what next? When it has half wave symmetry, what happens? So this is neither even nor odd, but it has got half wave symmetry. That means in the Fourier series representation, it will have only odd harmonics. Let's write that comment here. In the Fourier series representation, this will have only odd harmonics. Contains sine and cosine with odd harmonics. I'll just write it as Fourier series contains only odd harmonics. Odd harmonics. So this is the conclusion. So let's analyze few more waveforms. The more waveforms you analyze, the better understanding you will have. So what about this? So What about this? It's a very, very simple activity. So this is 1 here, minus 1 here, okay? So minus 1 here, 1 here. Clearly this is an example of an odd function. This is an example of what? Odd signal. So obviously if you try to find the DC value, it turns out to be 0. So first of all, it's odd. It's odd. Do we have any other symmetry? Do you have any other symmetry? Now for that, what I'll do is I'll check whether this has got half wave symmetry or not. So now what will you do for half wave symmetry? You have to consider the periodic signal in one fundamental period. So like this, you have to consider the periodic signal in one fundamental period and then shift this portion to the other half. I said shift this to the other half like this. So this is how it looks. Now you have to rotate this about x-axis. When you rotate this about x-axis, you get something like this. Is it overlapping with this? Yes, exactly overlapping. That means it has got half wave symmetry. It has got half wave symmetry. So I'll write plus half wave symmetry. Now, if it is odd, then what can you say is there are no cosine terms. There are no cosine terms. And when you say it's half wave symmetry, only odd harmonics are there. Now finally, what's the conclusion? In its Fourier series representation, you will have sine terms with odd harmonics. Because there are no cosine terms, there is no DC. So whatever you have is sine and what? Sine with odd harmonics. Let's write that comment here. So what do you have? We have sine with odd harmonics. The Fourier series contains sine with odd harmonics. Contains sine with odd harmonics. So let's take few more waveforms. There are few more interesting points that I have to discuss with you. So let's look at this. Let's look at this. This is periodic. You try to rotate this about y-axis, you again get the same waveform, right? You rotate this about y-axis, you get again the same waveform, meaning by it's a even signal. This is a even signal. The first point is that it's a even signal. It's a even signal. Can you tell us what is the DC value? How do you find the DC value? For that you have to integrate in one fundamental period and divide by the fundamental period. So let's analyze this waveform, which is like this. And again, you see the same thing, right? Same thing is repeating. Okay. So what do you feel is the fundamental period here? The fundamental period, you can consider the waveform from this point to this point. So minus pi to pi, that is 2 pi. The fundamental period is 2 pi. Let me write that. The fundamental period is 2 pi. Now try to integrate the periodic signal in one of its fundamental period and divide by 2 pi. Now no need to integrate from minus pi to pi by minus pi by 2 because it's 0, and no need to integrate from pi by 2 to pi because it's 0 again. You just have to integrate in this duration, that is minus pi by 2 to pi by 2. That means it is simply taking area under this. So what's the area under this? This looks like a rectangle. This looks like a rectangle. So the DC value is, how much is this width? It's pi. It's pi and the height is 1. So it's pi times 1 whole divided by 2 pi, which is 1 by 2. The DC value is 1 by 2. We said it is even. We said the DC value is 1 by 2. There is one more interesting point to this. Now to find that interesting point, what are you supposed to do is, you are supposed to remove the DC value from the waveform. What are you supposed to do? To find the other symmetry, to find the hidden symmetry especially, you need to remove or subtract the DC value. So how do you subtract? So here it's 1. So what is 1 minus 1 by 2? 1 minus 1 by 2 is 1 by 2. And here, look at this, and here it's 0. So what is 0 minus 1 by 2? 0 minus 1 by 2 is minus 1 by 2. So how does the waveform look after removing a DC value? Let's draw it. How does the waveform look after removing the DC value? Now once again let me tell you, this is 1. So for half of the duration it's 1, and for the remaining half it's 0. So when you remove like this DC value from this, what is 1 minus 1 by 2? It's 1 by 2. So the signal looks like this. It's 1 by 2 and 0 minus 1 by 2 is minus 1 by 2. So it looks like this. So after removing the DC, this is the periodic function. Now, is this having any additional symmetry? So let me first write, this is after removing DC value. So whatever we got, this is after removing the DC value. Now observe this waveform. Can you tell us, is there any other symmetry in this? So there is one symmetry here, check this. So this is the periodic signal, right? If you shift this, right? If you shift this to the other half, it looks like this. And then if you rotate this about x-axis, this overlaps with this. Meaning by this periodic signal, which one? This periodic signal has got hidden symmetry, and that is hidden half wave symmetry. So let me write that. So this has got hidden half wave symmetry. Which one? This person or this signal. So hidden half wave symmetry. Okay. So whenever you have some DC value, you are supposed to subtract it and then look at the resultant signal and then comment about the additional symmetries. So now just by looking at this, we understood that it is even. It is even. And then I calculated its DC value and I have removed the DC value. After removing this, I got this. So if you shift this portion, this particular portion to the other half, it looks like this. And then you have to rotate it about x-axis. Clearly, it is half wave symmetry. So if it is half wave symmetry, only odd harmonics are there. And in addition to that, it's an even signal. So you'll have cosine with odd harmonics, and there is also a DC value. So finally, what's the conclusion? In its Fourier series representation, what are the terms? The terms that are present, there is a DC. So we have got DC and cosine with odd harmonics. Cosine with odd harmonics. So this is the final conclusion. So whenever there is a DC value, it's better we subtract the DC value and then analyze this. Usually in the competitive exams, they give with some DC value, it's better we remove it and then analyze it. So let me show you a few more examples. Have a look at this. So what kind of symmetry is there? The first thing that I'll do is I'll first find DC value to check whether there is any hidden symmetry or not. So let's find the DC value. So this is the pattern that is repeating over the time. It's a periodic signal with the fundamental period being 1 unit. So this is 1 unit, right? So let's find the DC value first. So what's a DC value? You just have to integrate in one fundamental period and divide by that fundamental period. So what is integration of this? Integration of this is same as taking area under that. Okay. So it's like half base, this is base which is 1, and the height of this triangle is 2. So it's half base into height. So this is 1, the DC value is 1. It's better we subtract the DC value and then analyze the waveform. So let's subtract the DC value here. And once again, what is the fundamental time period here? The fundamental time period is 1 unit. Okay. So what I would like to do is I would like to draw the signal from minus 1 by 2 to 1 by 2. Right. So after removing the DC, let's try to draw the signal from minus 1 by 2 to 1 by 2. So have a look at this. So this is, let's say, minus 1 by 2, and let's say this is 1 by 2. So how much is this? This is 2. I want to subtract the DC value. So 2 minus 1. 2 minus 1 is 1. 2 minus 1 is 1. Now it's 0 here. 0 minus 1. 0 minus 1 is minus 1. Okay, 0 minus 1 is minus 1. Let's mark minus 1 here. So when you subtract, what happens is you get a resultant waveform like this. Okay, you are subtracting, so you get like this, and then this goes like this, and then like this. So now this is a signal after the removal of DC. Okay, this is a signal after removal of DC. So whenever there's a DC value, we usually remove that and then check for the hidden symmetries. So let's assume that this is like f of t. Right? What next? Rotate this about y-axis. Okay, rotate is about y-axis, rotate is about x-axis. Let's do that, and then we will comment about what kind of symmetry is there. Okay, so now I have to rotate this about y-axis. So this goes here, this goes here. So let's mark this. This is minus 1 by 2. This is 1 by 2. If you rotate this about y-axis, what happens? You get something like this. If you rotate this about y-axis, you get something like this. So what is this? This is f of minus t. What else we are supposed to do? We are supposed to rotate it about x-axis as well. Let's rotate this about x-axis. If you rotate this about x-axis, this goes down, this goes up. Let me draw this. This goes down, right, like this. This goes up, like this. Okay. So I have done the rotation about x-axis. Now let me draw it clearly. Let me use another color. So now when you rotate this about x-axis, this goes down like this. This goes up, right, like this. So now this is the rotation of f of t about which axis? X-axis. Now compare f of minus t with minus f of t. You need to compare f of minus t with minus f of t. Are they same? Are they same? Yes, they are exactly the same. Meaning by this particular periodic signal has got a hidden symmetry, and that hidden symmetry is the odd symmetry, right? The hidden symmetry is the odd symmetry. So finally, this periodic signal is odd. It has got hidden odd symmetry. That means in this Fourier series representation, there are no cosine terms, right? You will have sine terms. Now I have a doubt, does this have half-wave symmetry? Half-wave symmetry, let's check it. For half-wave symmetry, what we usually do? We shift this to the other half and then rotate it about x-axis. Let's do that as well, right? So this is having any half-wave symmetry or not? Let's check. I have shifted. I said shift, okay, shifted, and then I have to rotate this about x-axis. So when I rotate this about x-axis, I get a waveform. I get a waveform like this. Is this overlapping with this? No, right? That means it has no half-wave symmetry. It has got hidden odd symmetry. So finally, in the Fourier series representation, it will have DC, and because of this odd symmetry, it will have sine terms. Let's write that point here. Let's write that point here. So in its Fourier series representation, it contains what? It contains DC with sine terms. DC with sine terms. And I have seen whether this contains or whether it has half-wave symmetry or not. It doesn't have half-wave symmetry. So Fourier series contains DC plus sine terms. So whenever you have got a DC value, it's better we subtract that and then we analyze. Okay. So I'll take few more examples to make this discussion like a complete analysis. So have a look at this. The moment I look at this, when I rotate this about y-axis, you again get the same thing. When I rotate this about y-axis, you again get the same thing. So now, do we have any other symmetry? First of all, let me say that this is a even signal. Now after solving this many examples, you people should be in a position to directly answer this. So it's an even signal because rotation of this about y-axis is resulting in the same thing. What's the DC value? You can see that this is like a positive peak, this is like a negative peak, right? In the process of integration, the answer is 0. So the DC value is equal to what? It is equal to 0. Now I want to know whether this has got half-wave symmetry or not. For half-wave symmetry, what we usually do? Now consider this periodic signal and then shift this part to the other half. Shift this half to the other half. So when you do that, what happens? Let me show with some dotted lines here. Shift this to the other half. After shifting, you have to rotate this about x-axis. So if you rotate this about x-axis, you get, so when I shift this to the other half, let's see what happens. So this is what I get. So I have shifted. What next? you have to rotate this about x-axis. When you rotate this about x-axis, you get something like this, okay, which is exactly overlapping with this. That means it is not just even, its DC value is 0, it also has got half wave symmetry. The third point is, okay, the third point is it has got half wave symmetry. Now what's the conclusion? Whenever it is even signal, okay, whenever it is even signal, it has got only cosine terms, right? DC is also 0, so it has only cosine terms. And in addition to that, if you say it's half wave symmetric, then you will have only odd harmonics. So I'll write that the Fourier series contains cosine terms with odd harmonics. So what's the conclusion? The Fourier series contains cosine with odd harmonics, okay, with odd harmonics. So now I have the one more example. Let's see whether you will be able to answer it or not. So have a look at it. What is given to you is a periodic signal is given in one of the time period, right? The complete periodic signal is not mentioned to you. What is given is just a periodic signal in one fundamental period, and you are supposed to comment about its DC value, right? What kind of symmetry is there? Is it even, odd, or do we have any half wave symmetry? So how do you get that? Now the first step that you have to do is try to draw the periodic signal. If it is given in one fundamental period, just repeat these portions to get the complete waveform. So the first thing that I'll do is I will draw it. So for drawing that, I'll just repeat this. So let's mark something like this. Let's say this is 2. Let's say this is 1. Okay. Let's say this is 1. Let's say this is 0. Let's say this is minus 1. I just have to repeat this. Okay. So take this, put it here. So when I put it here, I get a waveform like this. Okay. So let me draw it neatly. So what do I get? I get a waveform like this. Okay. Now you keep on repeating that. So if you keep on repeating that, you get a periodic waveform like this, right? So this is what I get after repeating it. Now I want to check what's the DC value, what kind of symmetry is there. So the first comment is about its DC value. So how do you find its DC value? You just have to integrate this periodic function in one fundamental period and divide by the fundamental period. So obviously here the width is 1, here the width is 1, that means its fundamental period is 2 units. Right? So let's try to find the DC value. So here the width is 1, so it's 1 into the height is 3 plus, what's the width here? The width is again 1, right? And here the height is like minus 1, so it's 1 into minus 1 whole divided by what? Whole divided by 2. So it's 3 minus 1, which is 2, 2 by 2 is 1. Therefore the DC value is 1. Now you can comment about this after subtracting the DC value. It's better we subtract the DC value and then check for the hidden symmetry. Let's draw that. Let's draw that. So for that, what are you supposed to do? Subtract the DC value. So how will you do that? So here, since it's 3, it's also 3 here. So it's minus 1 here, so this is minus 1. You just have to subtract the DC value. So how do you do that? 3 minus 1 is 2. That means half of the duration it's 2, and for the other half, for example, this is minus 1, right? So minus 1, because I said subtract the DC. So this is already minus 1, minus 1, minus 1, minus 1, it is minus 2. So for half of the time it's 2, for the other half it's, okay, for other half it's minus 2. Keep on drawing that. So here it's 2, okay. So let me use another color here. So it's something like this. Okay. So now comment about the symmetry. This is 2, this is minus 2. Clearly it's an example of odd signal. It's an example of odd signal. If you want, you can do whatever procedure we have done earlier. It is odd, not just odd, it has got half wave symmetry as well. So how do you check that? For that, what are you supposed to do is, you are supposed to, let's say, shift this portion to the other half. Let me shift it. When I shift, I get this. Apart from that, I should also rotate that about x-axis. if you rotate this about x-axis, it exactly maps with this or exactly overlaps with this. So it has got hidden odd symmetry as well as half wave symmetry. So the conclusion is that it has got, the first thing is odd symmetry. The second thing, it has got half wave symmetry as well. It has got half wave symmetry. So what's the conclusion? The conclusion is that in the Fourier series representation, it has got the DC value. It also, like the signal exhibits the odd symmetry because of which there are no cosine terms. In addition to that, it is half wave symmetry. Now I can say that there is a DC value sine with odd harmonics. Let's write that comment. The Fourier series contains what? DC along with sine odd harmonics. So we have DC plus sine with what? Odd harmonics. Okay. So now this is what we have. So now what did we do in today's live session? We looked at what is the Fourier series of a periodic signal, and after that we have analyzed what happens in the case of even, odd as well as half wave symmetry. Let me quickly show you what we have discussed in today's live session. So we started with, what's a Fourier series, right? So how do you write the Fourier series of a periodic signal? So we have mentioned it. We looked at what is A naught, what is An, what is Bn, and if I give you a even signal, right, what happens to this A naught, An and Bn? So this table is very, very important. So this is for what? This is for odd, and this is for half wave symmetry. And if, like, in most of the competitive exams, you can see that there are questions from this table. So I hope after watching this video, okay, after like going through this video, you will definitely now understand how to check the even symmetry, how to check the odd symmetry, and the most important thing where the most of the students confuse, that is half wave symmetry. Half wave symmetry deals with what? It deals with the shifting operation, right? The shifting operation as well as there is a rotation about x-axis. I hope these examples or whatever we have discussed, it will definitely help you in identifying the symmetries. Sorry, comments? So that's it for the today's live session.